All right, so this lecture we're covering sound and hearing, and I hope that I've communicated last lecture how important waves on a string are. We spent some time on that. The truth remains, however, that transverse waves are only half the story. If transverse waves were the only kind of wave, you would not be able to listen to this lecture, a lecture as it happens on sound. So please sit back and enjoy experiencing this meta lecture as we traverse the physics of sound. Some topics will be familiar from last lecture, but others, such as why we hear beats and the Doppler effect, may be entirely new. So sound waves, we can define sound in the most inclusive sense as longitudinal waves in a medium. Note, however, that these longitudinal waves do not need to be in air or within the frequency range that we can hear, which happens to be from about 20 hertz to 20,000 hertz. If you are curious. This frequency range that we can perceive is called the audible range. Sound waves with frequencies higher than the audible range are called ultrasonic, while those with frequencies lower than the audible range are called infrasonic, a less common term, I think. Sound waves usually travel radially out from the source with an amplitude that diminishes with increasing distance. But we'll start with the limiting one-dimensional case to build up our mathematical description. And you'll be pleased to hear that much of the math for transverse waves transfers nicely to the longitudinal case if we simply consider the displacement of the particles, y, as a function of x and t. If we consider that to be parallel to the x direction propagation of the wave. So what does that mean? So if we have a longitudinal wave, the wave is going to be traveling along that direction. Think of sound through air, or you can think of longitudinal fluid wave. And also the displacement of particles in a longitudinal wave is going to be this way, back and forth. And so before, for a transverse wave, we had displacement this way, and the wave was traveling that way. And so we had two distinct axes to work with. But on this one, what we're going to do is we're going to label y as a function of x and t as the displacement of the particles, which is in the same direction as x, the direction of travel of our wave. So that may feel like a little bit of an uncomfortable trick, but it does allow us to reference the position of the particles separately from its displacement, even while they are each along the same axis. And if we accept this, it simplifies things a ton. And we can describe a longitudinal wave in our familiar form, y as a function of x and t is equal to a cosine kx minus omega t. While this works just fine, it turns out that it's sometimes even more useful to describe sound waves in terms of pressure variations along the direction of propagation. So we're going to use both forms. So we're not ditching this guy, but we're going to introduce a new one that is sometimes more useful. So let's say, I'll do this. Let's say you have a tube of air or fluid of some sort, like this. And we're going to represent the particles as being evenly spaced here, like this, as best as I can do. If we have this tube of air at atmospheric pressure, then we momentarily compress it and then uncompress it with a piston from the left. Then we get a region of higher pressure traveling through the cylinder, which is a longitudinal wave pulse. So let me represent this for you. So now we're going to have a piston on the left side of this tube that pushes in. It's a piston, which means that it compresses that first air molecule right up next to the next one, and the rest have not experienced the wave pulse yet. And if you go to the next sequence here, a moment later, the piston has retreated, and we have the original air molecule has moved back that way, but this guy has moved up close to the next one, and that's where the current wave pulse is. And if we were to continue, you would just see it traveling. And so the wave kind of, oops, wow, sweaty hands maybe. The wave starts here and then moves there, and if we were to continue, it would just propagate through the tube, right? So it's going this way. And also the particles, which I believe I represented in yellow before, they're going back and forth, right, as it travels. So for a sinusoidal sound wave, the pressure fluctuates above and below atmospheric pressure, which we'll say is, get rid of these guys, given by this, a lowercase p sub a. And it fluctuates above and below this atmospheric pressure sinusoidally with the same frequency as the displacement of the air particles. So we can come up with a separate mathematical description that's equivalent to this one up here that talks, instead of displacement of the particles, it talks instead in terms of small pressure regions traveling through the tube and changing sinusoidally. So let's build that up. So we can express this wave in terms of the pressure, the position of x and t. So what we're wanting is p for pressure as a function of x and t. That's the amount that the pressure differs from atmospheric pressure at a given position and time, right? So atmospheric pressure, this, oh my goodness. Atmospheric pressure, PA, is the reference. Right. So let's say our tube has cross-sectional area S, and let's consider a small segment of length delta x. So you'll see that there's some familiar techniques that are used in math and physics and other fields that you will see these kind of techniques pop up more and more and more. And so to build up complex systems, oftentimes we find ourselves starting with little bits of the system and considering how those little bits morph over time. So if we take little slices or a little particle or a little tiny volume, then it'll tell us a lot more than we realize when we propagate that out. Oops. Okay, so there we go. I'm going to attempt to make one of these guys and another one. And I'm going to tell myself that taking the time to create this is not frustrating to you, but rather pleasing to you because I'm creating a nice diagram. If you disagree, maybe you can skip ahead, I guess. But we're going to consider this nice little slice here, right? And so we have an area S, right? And we have an axis down here, which is the x-axis. And that means that where this slice exists is what we'll call x, and where this slice exists is what we'll call x plus delta x, right? All right, so when no sound wave is present, our small cross-sectional slice has volume S times delta x. And that's what's shown in blue there. When a sound wave hits the slice, the left end of the slice is displaced from the position x, an amount, so we're talking about now, this guy is displaced an amount, we're going to call him 1, right? So call him 1, and then we'll call that guy 2. I'll Just label that right there. And when a sound wave hits him, the left end of that slice, all those particles that exist at that cross-sectional area there, is going to be displaced an amount y1 as a function of x and t, right? At any given position x and at any given time t, you can find what they're doing. And then the right end, similarly, is just going to be a separate function. Why a separate function? Well, even though it's a tiny, infinitesimally small slice, it's still, we're going to consider that the left face of that slice moves differently from the right face, because that's what pressure is all about, right? So if you have, let's see, I'm going to do my best to represent this. Yeah. If you have your x-axis there, and you originally had your you originally had the left end of the tube there at x. Well, now he's going to move an amount, left or right, but I'll represent it to the right, over here, which that's not the same size. Try to get it just a little closer, but I won't get too lost in the details here. All right. Oops. All right. So now he's going to exist in a different place. So this distance here, I'm going to do it in green here. This distance, let me do this differently. Sorry. Okay. If our slice was originally, we're zooming way in, if our slice was originally like this, right? And it had this width here, whereby this is x plus delta x. There we go. That's our original slice. This is our 1 left face, and this is 2, our right face. We are considering the fact that it will transform at a different time a little bit into this white interval here. So this is now somewhere new, and this is still 1, but at time 2. I don't know how to represent that exactly, but you know what I mean, because it has moved from there to there. And we have the right face over here, we'll say is moved this way. And that, again, is still 2. And we have the entire little slice has now become this lengthened piece here. All right, and the right face also exists at a new place, right? So this distance from here to there that the left face moved is going to be given by y1 as a function of x and t, and the amount that the right face moved is going to be given by y2 as a function of x and t. Seems really granular, I know, but it will help to build this foundation from the ground up, and then you can use the results of it with full knowledge of where it came from. All right, so note that each end is not displaced an equal amount, right? We ended up with a lengthened segment here, and ignore the fact that, you know, it's bigger here than it is there. My line kind of went up a little bit. Ignore that. And so what you find is that because of this lengthened interval here, it causes a total volume change of the slice, and we can find that volume change. That volume change, delta V, is given by S y2 minus y1. In other words, S y x plus delta x and t minus y x and t. All right, and just like before, we're going to take the limit as something goes to 0 and turn that into calculus so we can find a derivative. And so we're going to take the limit dv over v, right, per volume. Limit as x goes to 0 of this whole thing, s y x plus delta x and t minus y x t. That's our numerator. And then the per volume, we said earlier that the volume of this thing, right, of this slice, volume is equal to the area of the face times the thickness of the slice. So S times delta X. And so we're going to come down here and plug that in. S times delta X. That's the V at the bottom. And taking that limit, using calculus, you find that you can express this as the partial derivative of y as a function of x and t with respect to x, because the s's cancel. And if x goes to 0, or delta x goes to 0, that's what that should be. As delta x goes to 0, then the interval gets smaller and smaller and smaller. So basically we took some finite but tiny slice and we considered what's going on at each side. And if we just flatten it more and more and more and more and more as the width of that, the thickness of that slice approaches 0, then we get this partial derivative of y as a function of x and t with respect to x. So there's one last component that's needed to bring this together, because this isn't exactly what we set out to get. This is a mid-step. What we want is this guy, right? We wanted the pressure as a function of x and t. What we have is this partial derivative, and we're still talking in terms of y as a position of x and t, so not exactly what we're setting out for yet. So what we need is what hopefully you at least saw reference to in your Physics 1 course, which is this quantity called the bulk modulus. And it's in reference usually to stress, mechanical stress. And bulk stress is just is pressure differences on a volume. And so the bulk modulus, if your course did not cover that, it's a pretty simple concept. Just flip back to that page in the book and give a couple paragraphs to read. But we have the bulk modulus given by the negative of the pressure as a function of x and t divided by dv per volume. The change in volume per unit of volume. All right, so it relates these two things. And so therefore, we can plug some of this stuff in, yeah? So we have the volume, the change in volume per volume down there, and what we want is A. What we want is here, right, that pressure is a function of x and t, and so then we can just rearrange all of this to find that the pressure is a function of x and t is equal to negative of the bulk modulus times our partial derivative. All right, and we are considering a sinusoidal wave, and that sinusoidal wave that we can plug in here to find what this evaluates to, we're going to say our wave, function of x and t, is equal to a cosine kx minus omega t, right? That familiar old thing that we wrote up here somewhere. Yes, this guy, right? So we're going to take that familiar old sinusoidal wave, and if you plug that in, then this simply evaluates to bk a, all that comes out, sine kx minus omega t. Do slightly better k there. There. All right. So now we have two different expressions for a wave. We have it in terms of position, and we have it in terms of pressure. This is going to be really useful. So this is our pressure one, and this is our displacement one, right there. So position, and this is in terms of pressure. Both are useful. So now, let's take a look at them. So I'm going to see if I can bring in a graphic so you won't have to suffer through my drawings forever. Let's see. Update. Bear with me. Okay, well, I'm having to sign. Oh, there we go. Okay, here we go. All right, so now if I paste that in, we'll see it momentarily. It syncs. Okay, so have a look at this while I navigate back over to where I need. Jeez. All right, so this gives a graph of both the position-based wave and the pressure-based wave. So they're both describing the same wave, but they're describing two completely distinct physical quantities that are happening as a result of the same wave. One is considering the particles as they're moving, right, left and right, and the other one is considering the pressure. It's a different type of expression, but they're both equivalent because they're both the same, a phenomenon based on the same wave that's going through. So we can kind of just see the same wave through two different lenses is what it's like. So let's look at these three plots and see if we can connect the two descriptions to our understanding of what's happening physically. So notice specifically that the position description up top here and the pressure one are 1/4 out of phase, right? So if you bring this guy down, starts at the top. I'll use a different color because that's hard to see. Pink. He's at the top here, and if you trace that down, he's right midway, right? And then this guy's at the top 1/4 phase later, and he's midway. So they're 1/4 out of phase. So that's something to note. We can also see that the maximum pressure fluctuation occurs when, well, I guess we can see this from this expression more. This expression here. When is the maximum pressure going to occur? Well, sine can only be at max 1, and any other thing that's plugged in, it'll be less than 1, right? And so the max pressure, evidently, is when the sine business is equal to 1, in which case we get a pressure of BKA. So that's worth writing down. So pressure max is equal to BK A. That kind of looks like an R, and I used to be frustrated with instructors that did that, but it's hard to distinguish between lowercase and uppercase k, and they both become relevant, so you eventually get in the habit of writing these weird k's. So that's max pressure. And also, if we look at the plots of the two expressions, I'll pull that back up here, we can see that the pressure amplitude is directly proportional to the displacement amplitude, which makes sense given the two mathematical expressions. Directly proportional. So higher frequency waves, which means they have a larger wave number, which means wave number k, so large k, and k is equal to 2 pi frequency, and so that means higher frequency. Because it's so useful to represent waves in terms of this k and omega, you'll start to kind of connect in your mind what a large k means and not have to kind of think through it. But for now, we'll go back to connecting exactly how it's related to frequency. But anyways, if you have a higher frequency wave, that means that more things are happening per time, right? You have larger pressure changes for a given amplitude because the pressure still fluctuates through the same full amplitude, but in less time, right? So if you have, in terms of displacements, it's easy to think about this. If you have particles that are displacing from left to right here, if they have to do that in 2 hours, it's going to look a little bit different than if they have to do that in 2 seconds, right? So it's higher, it's larger displacement changes, right? Which would be velocity, higher velocity of the particles. But in terms of pressure, it maps just the same. You have larger pressure changes for a given amplitude being this full distance here that the particles will be traveling through if we're talking in terms of displacement, or the pressure region if we're talking in terms of pressure, because it's still fluctuating that same amount, just in shorter time. Also, one final conclusion here is if the material is very hard and less compressible, you may be familiar, or I will just tell you that means that the bulk modulus is large. So B is larger for harder, I'll put that in quotes, harder materials. And what that means is, by harder, is just less easily compressed, right? So if you have some volume, right, and you have bulk stress on it, that means that you have pressures in all directions. For a given force on all sides, how much does it deform? That's what the bulk modulus is talking about. And so if it doesn't deform very much, think about if you just push on concrete or rock or something, very high bulk modulus versus jelly or something. Then what that translates to in terms of our equations is if B is large, then the amplitude, BKA, of the pressure wave is that much larger than the amplitude A of the displacement wave. So let me put this just because we're referencing back and forth. So that's pressure, and then Y, X, and T is equal to A cosine kx minus omega t. Those are the two expressions. I know we wrote it up top, it's no different, but I'll write it here. Displacement. Just so you can compare. So looking at the amplitudes then, the pressure amplitude is BKA, and the displacement amplitude is simply A. So you have this bulk modulus component that's involved in the pressure, in the pressure expression. And so if B is large, then the amplitude BKA of the pressure wave is larger than the amplitude A of the displacement wave. So what this means physically is more pressure is required to displace the particles in a harder material a given amount than for a softer one, right? So you may be able to move it, but not as much for a given material. All right, so hopefully that gives some foundation for these two different ways of thinking about longitudinal waves. Probably came as a little bit of a surprise. We're talking in terms of pressure, but it is very useful. So next we're going to talk about actual sound and the speed of sound waves and other things.